In the previous video, we built an intuition for what word embeddings are using a simple real-world example. We also built our own embedding model from scratch in Python, and we saw how two words which appear in similar contexts may have similar meaning, and so they are brought close together in the embedding space. Now, while training your own embedding model from scratch can be helpful for domain-specific tasks, usually engineers don't do that. Instead, they rely on pre-trained models which are widely available in the market and has learned rich semantic representation from massive amount of text online. But that raises some interesting question. How do modern embedding models understand context? Or how do they generate single embedding vector for the entire sentence or document instead of generating individual embeddings for each of the words? And with thousands of embedding models available in the market, how do engineers even decide which of the embedding model is most suited to their use case? And that's exactly what we will explore in this video. Hi, I'm Jyotsna and welcome to the Hidden Layers. I recently started this channel to share everything I have learned about AI over the past 7 years. So if you are from software background and looking to switch into AI related roles and preparing for interviews, or if you're someone who is just curious about how AI works under the hood, you're in the right place. Now, here's what we will cover today. We begin by understanding why static word embeddings, despite being so revolutionary, are no longer sufficient for most real-world NLP applications. Then we will see how transformers solve this limitation and how they produce contextual embeddings. Next, we will learn how to generate embeddings for entire sentence and documents and explore some of the most popular open source embedding models available on Hugging Face. And we will also use one of them in hands-on Python example. And finally, we will discuss key engineering trade-offs you should consider while choosing a model for your own use case, such as model embedding dimension, model size, retrievable quality, inference speed, etc. So, without further ado, let's dive in. So, there are essentially three failure points of static embedding models, and which is why they are not used practically as much for real-world use cases. So, let's just go over them one by one. First of all, static embedding models assign static word vectors to each of the words present in the vocabulary, and so they pay no regards to the context, or so to say, the sentences in which the words are appearing. And so if a word has multiple meanings, then there is no way a single fixed length vector can capture two different meanings depending on the words around it. And second limitation is that word embedding models do not have any sentence level understanding, meaning that it assigns word vectors to each of the words present in a sentence. But what if you want to understand the meaning of an entire sentence as a whole? And now third is that it cannot handle out of vocabulary words. Since static embedding model is essentially a fixed dimension matrix created during the training process, and so it only has the word vectors available for the words which were available during the training. And so it cannot generate word vector for any out of the vocabulary word. And so now all these limitations led to the creation of something called as contextual embeddings, which is basically, as clear by its name, honors the context in which a word is appearing and assigns the vector to it dynamically. So what does that mean? Let's understand using these two example sentences. You see how the word book has got two different meanings here? And so we need a way so that we can assign two different word vectors depending on the context in which this word is appearing. Which takes us to transformer models. If you haven't heard about transformers architecture, then don't worry, I'll be making a complete series on each of the building blocks of the transformers architecture, as it's the key foundation for understanding all the modern LLMs today. But for now, let's just say that transformers architecture has components which enable the capturing of the entire context while creating the word vectors. And so here, when the first sentence passes through this transformers embedding model, the contextual embedding which is created is something like this. And then we pass the second sentence. And here is the representation. And so you see how these two vector representations are different from each other. D here is the embedding dimension, as you might have already guessed it. And this context-based word vectors assignment was essentially possible because of attention block in the transformers model. We will be covering that topic in detail in the Transformers series. But for now, focusing back on embeddings, BERT is a special kind of transformers model which is essentially used in industry for all the different sorts of embedding models. It's mainly the encoder part of the encoder-decoder transformers model, and it has the capability of capturing the context in a bidirectional fashion. And so for any word, it looks at its left and its right to get the entire meaning of the sentence to decide what should be the word vector for our word of concern. It also pays regards to the position of the word in the sentence. And so it's essentially able to also capture the order of the word. So sentences like I love pizza and pizza love I, both the sentences are different in terms of order, and so the word vectors assigned to them will be different. So now we have some understanding of how transformer models help in capturing the context while creating the word vectors. Let's talk about how can we capture the meaning on a sentence level. So now suppose we have this sentence and we try to get the word vector for each of the words present in the sentence by passing it through the model one by one. Great. So now we can see that we have captured all the vectors for each of the word present in the sentence. So now can you think how can we have a single vector to represent the entire sentence? You might be thinking that we can take an average of the word vectors present for each of the dimension, and that should suffice to represent the entire sentence. And that's partially true. Another way to pull the information could be taking the max value for each dimension, and that could also give a single vector to represent the entire sentence. There is also a third way. BERT models have special kind of token or input, so to say, which captures the entire sentence's meaning in its own embedding. Meaning the output vector created by the model for CLS token represents the entire sentence's meaning in its own word vector. However, even this clever idea has some limitations. So first of all, mean pooling and max pooling, although being simpler to implement, has limitations because they do not capture the order of the words present in the sentence. So sentences like I love pizza and pizza love I will essentially have the same sentence level vector, which definitely makes it inaccurate. And now CLS token pooling, although being less computationally expensive, when tested to find the semantic similarity between two sentences, performed very poorly. And so all these three techniques, although being intuitive, do not really help much in real-world use cases. So you may wonder, why did I mention before that BERT models are actually used in industry? It's because although the pooling methods did not work, BERT models still are able to capture the context level understanding of the sentence. And so a new variant of BERT models, which is called SBERT or Sentence BERT, were developed. And as mentioned in this paper which introduced it, it's essentially the modification of the pre-trained BERT network with an aim to focus on the task of deriving the semantically meaningful sentence embeddings, and so which can be used for any number of different downstream tasks, such as finding similarity between two sentences, retrieving documents with similar meaning, etc. So the training objective for a sentence BERT model looks something like this. The two sentences which are similar in their meaning are basically brought close together by training the model. The dissimilar pairs are basically pushed far apart. And the closeness of two sentences is measured by cosine similarity. And this is essentially a contrastive learning process, which basically fine-tunes a BERT model to derive the semantically meaningful sentence level embeddings. Say we have this use case where we have bunch of incoming tickets coming to a customer support service, and we need to find the duplicate tickets so that we can have better ticket management and can also save agents time. So let's work through this and see how embedding model can help us solve this use case. And now you may wonder which model exactly to use for this. There are thousands of open source pre-trained embedding models available today, and choosing the right one is not always straightforward. And so that's where MTEV comes into picture. MTEV, which stands for Massive Text Embedding Benchmark, is a standardized benchmark that helps engineers compare the models and select the ones that's best suited for their use case. It provides ranking for all sorts of embedding models based on different benchmarks on tasks and datasets. And these are the different tasks on which the benchmarks are created. This is taken from the original paper itself. We can see that the tasks like clustering, retrieval, semantic text similarity are some of them. And since embedding models are usually fine tuned for some specialized tasks, so they may be better at one task than others. An MTV leaderboard also helps us in selecting the right model which is suited for our use case, which we'll see now. Okay, so now let's just try to find an embedding model for our use case using MTEV leaderboard. So this is hosted on Hugging Face Space. I will link this down in the description. First of all, since we need an embedding model for English language, so we can actually click on this. Now you see all the different models here. There are so many different open source as well as proprietary models. So now let's just first look at the right hand side. It provides a suite of filters which we can use to basically narrow down our range here. Now suppose we need a model which we can run easily on CPU. So the typical range for that is around 150 million parameters. So let's just tune it. Model size is something which tells us the number of parameters the model is going to have. Now we see that instruction tune, we just leave these filters for now. Instruction tuning is something with the model which is fine tuned using instruction type dataset. And now let's just select this sentence transformer so that we can use the sentence transformer library to basically use the model. Now, also, we have the different modalities of data since right now we only care about the text data. So let me clear this filter and select just text. Okay, so now we have all the filters selected. Let's go to benchmark scope. As we discussed earlier, we have these different task types on which the models are benchmarked. And now since the task at hand is basically to identify the semantically similar sentences, so let's just select this one, which basically re-ranks the model again based on this benchmark. Now we come back on the left hand side and we see the models re-ranked based on the filters which we had selected. Now this model looks pretty fine to me. It has got 109 million parameters and the scores also look okay. Okay, so now let's just click on the first model. Now on the right hand side, we see the emitting dimension to be 768 dimension, which is pretty decent for our use case. And then the memory is 418, which is basically dependent on the number of parameters and the parameter size. So now let's just go ahead and use this model. So you can just open Google Colab here and let's just first import sentence transformers. Okay, so now let's just initialize our model. Sentence transformer. Then let's just look at the model name. Okay, so let's just say we have. Okay, then now the model is loaded with all the tokenizer and the other files. We will talk about tokenizers in a future video, but I hope you have a basic understanding. It's basically breaking down our text into smallest unit. It could be a word or even a fragment of a word. Now I've created just these few examples of support tickets. So first step is going to be embedding these tickets individually. So embeddings equals the model encode, and then we take these tickets and we convert these embeddings into their tensors. So now let's just check the length of one of these embeddings. So length of embeddings. Great, we have 768. This is what we have as our embedding dimension, right? Okay. The embeddings are created now. As a next step, what we need is to find pairwise embedding cosine similarities so that we can check which two tickets are duplicate. So first of all, let's just also import util. Now using this, we can have the cosine similarity for each of the sentence pairs. Okay. Let's just see how it looks like. Right. See how many sentences? We have 8 tickets and just see the shape of this. Yes. So we have 8 cross 8 matrix here, which basically defines the similarity scores of each sentence with the rest. So on the diagonals, you can see that all the elements are 1, which means that the cosine similarity of the sentence with itself is of course 1, which basically makes the diagonals 1. Now I have a small script here which finds out all the sentence pairs with a semantic score with threshold above 0.75. So let's just run this and let's see the pairs. Right, so we now found the pairs of support tickets which were similar to each other, hence they could be identified as duplicate tickets. So now if we sort them and just format the printing, so now we can see the different pair of support tickets which could be potentially duplicate. And this we found using our embedding model, which was perfectly suited for this. So this was an example showing how you can select an embedding model for your own use case using MTV leaderboard. And I hope this was clear, and you can also try out finding a model best suited for your use case. Now, knowing about embeddings conceptually and knowing how to use it for industry use cases, those are two different things. And so it's imperative to choose the right model for your own problem statement. And so whether you refer to MTV leaderboard to find the best embedding model suited for your use case, or you simply just want to evaluate a model which you have at hand, here are 5 things which you should consider while evaluating. First of all, what kind of data am I working with? Is it only English or any other language? And if your application needs to handle multiple languages, you may want to use a multilingual model. Secondly, what problem you are trying to solve? A model that's great for semantic search is not necessarily best choice for the duplicate detection or classification. And so, benchmarks like MTV can be really helpful in identifying that. Next, think about the deployment constraints. Do you need real-time responses, or can you afford a larger model running on a GPU? Sometimes, speed could be more important for you than accuracy. And then, we can also check if our use case is domain-specific or generic in nature. Having a domain-specific use case may require you to use a specialized embedding model which is fine-tuned on that domain-specific data. And finally, there's the cost. You can either self-host an open source model which gives you more control, or use a proprietary model API like OpenAI, which is just easier to get started with but comes with an ongoing usage cost. And so, there really isn't a single best embedding model. The right choice always depends on your data, your use case. And once you understand these trade offs, choosing an embedding model becomes much more systematic rather than just picking the one that tops the leaderboard. And that's a wrap for this video. I hope you now have a much better understanding of the topic. And if you spend some more time on your own, you will be able to answer any kind of interview questions and can also apply for real world use cases. Embeddings are the foundational building blocks behind every modern AI systems. And understanding them brings you one step closer to understanding every modern application built so far. And if you found this video helpful, then please show your support by liking the video and subscribing to my channel. And thank you for watching. I'll see you in the next one. Bye.